By solving this first sample problem, it will set the basis for us to understand how to calculate the equilibrium constant for some species at equilibrium. In this problem, we are having 0.02 mole of gaseous phosphorus pentachloride in a 2-liter flask at 170 degrees Celsius, and it is allowed to sit until equilibrium is established. So inside of this flask we're having that amount of phosphorus pentachloride, and after equilibrium is established, this is the concentration of chlorine that was present. We now asked to calculate K for the decomposition of phosphorus pentachloride at this temperature here. In these types of problems, we are dealing with change in concentrations of species, but the concentration of this is not given. However, we are given its number of moles and its volume. So using this formula, we can find out its initial concentration, and that is equal to that number of moles there divided by its volume. So the initial concentration of the phosphorus pentachloride is 0.1 mole per liter. What we do now is establishing what is called an ICE table. ICE is an abbreviation for the following words: initial concentration, the change in concentration, and the equilibrium concentration. So we shall now go back to the problem and see what other information are provided. We have just found the initial concentration of phosphorus pentachloride to be equal to this. And now they're also telling us that at equilibrium, that is the concentration of chlorine that was established. So go back to our ICE table now. Let's see what we can insert. So that's the general equation here that shows how phosphorus pentachloride decomposes to give you phosphorus trichloride and chlorine. Its initial concentration was found to be that. But initially, we didn't have any of phosphorus trichloride nor any chlorine gases. If you look at this row here where change is mentioned, what happens is that as reaction goes on, the concentrations of the species change. And the way that happens is governed by the mole ratios of the reactants and products. For example, in this case, we see that every 1 mole per liter of phosphorus pentachloride that decomposes, we get 1 mole per liter of phosphorus trichloride and 1 mole per liter of chlorine. And because everything is in the 1:1:1 mole ratios, but because it is a reversible reaction and it does not go to completion, only a small amount X gets decomposed. So we shall represent that by a change that is called minus X, because we are removing things from this area here. But at the same time, an equivalent amount of phosphorus trichloride and chlorine is produced. That is why we're going to say plus X and plus X. So at equilibrium, we will have whatever concentration of phosphorus pentachloride present initially minus what was changed. And that is represented by this quantity here. And of course, in the end, we'll have X and X. But we do not know what those are. However, we have been told that at equilibrium, the concentration of chlorine was found to be 0.004 mole per liter. Verify that by going back to the question. That was the concentration of chlorine that is found at equilibrium. But according to the mole ratios, this is equal to that. So if you knew what that was at equilibrium, which is this, then phosphorus trichloride should also be the same. Another mathematical operation that has been carried out was to find the final concentration of phosphorus pentachloride, which turned out to be this. Let's see how they got that. We knew that the equilibrium concentration of phosphorus pentachloride is equal to that quantity here minus what X is. But we knew that X is equal to that value here. So subtracting this from what was there initially, we ended up with that to be the final concentration of phosphorus pentachloride. Now we know all the quantities that are at equilibrium. So if this is our reaction here, we all know how to express the equilibrium constant expression for that, which will be equal to concentration of that times the concentration of that over what the concentration of PCl5 is. Inserting the values for all of these into that expression there is going to be what these are, that there and that there, divided by what this is, which is this, okay? And this is what it turns out to be the equilibrium constant for the decomposition of phosphorus pentachloride at 170 degrees Celsius. Note how in every case, you're going to see this in every case, equilibrium constants do not have units. So quick review. If you're given a certain quantity of the initial reactant in a certain volume, the first thing you have to do is to find its initial concentration. What they will do also is providing the concentration of one of the products, and that will enable us to find the concentrations of all the species at equilibrium. First of all, you put your ICE table. We know this is the initial concentration. These are 0. Then the next table shows how the changes happen. The change is going to be minus X plus X plus X, because for every 1 mole per liter of that decomposes, you get a corresponding number of that and that. If you have a small quantity, X, you subtract it from that, and you must get the same quantities here, all right? But we were provided with a concentration of chlorine, which was that, and that enabled us to find what PCl was, because these must be the same. And knowing what X was, we then eventually found the final concentration of this, because we took that and we subtract X, which is this, and that's how we end up with it. Putting all of those inside the expression there, we ended up with that. Next problem. Again, we are being provided with a volume and a certain number of moles of hydrogen iodide gas that is placed inside that flask there at this temperature here. And it is allowed to sit for some time until equilibrium is established. Of course, this breaks up to give you some amount of hydrogen and iodine. Again, like the previous problem, they're giving you what is the final concentration of one of the products, which is equal to this for iodine. And you're asked to calculate the equilibrium constant for hydrogen iodide decomposing at equilibrium at this temperature. Again, like we did in the previous problem, we find the initial concentration of the hydrogen iodide by taking its number of moles, and we divide by liters, and it works out to be equal to 0.080 mole per liter. Next thing we do is to establish the equilibrium equation to show how hydrogen iodide decomposes to give hydrogen and iodine. Note how this is slightly different from the one before. Now you're having 2 moles per liter decomposing to give 1 mole per liter and 1 mole per liter here. Had this gone to completion, but knowing that it is a reversible reaction, that does not happen, only a small quantity of that will decompose. But now we have a different stoichiometric coefficients for these. We are getting 2 moles of this producing 1 mole and 1 mole. So we cannot say minus X will give me X and X. You have to remove twice that amount. So establish our IC table that shows the initial concentration with 0 of these, right? Then the next table is going to show us, you don't need to draw these tables, this is for teaching purposes, right? Next table shows how the changes happen. For every 2 moles of that, you get 1 mole of that and 1 mole of that, but we do not know how much really decomposes, so we let it be 2x. So look at this now. 2x of this is going to break apart, and you're going to get equal number of that and that, which you say is x and x. They have given you that for the final concentration of iodine. So the point is made that because these two here are the same, the hydrogen must also be that. So this is iodine, which is here. The hydrogen must be this. If you go back to the table before, we are removing from that 2x. So from this, whatever value of x is, we multiply it by 2 and remove it from that. And that's what we've done here. We say that x is equal to that, as is provided here. Therefore, 2x must be equal to that. So the final concentration of hydrogen iodide will be equal to whatever this is, minus that value there. It turns out to be this. And this is the final concentration of the hydrogen iodide. Now we know all the equilibrium concentrations. We establish our K expression, which is equal to concentration of that times the concentration of that divided by the concentration of this to the exponent 2. And when you do the math, it all turns out to be equal to 0.020. You can repeat the video to get a more profound understanding of how that is done. Now I'm going to point out something to you here. This is the equilibrium constant for the decomposition of hydrogen iodide into iodine and hydrogen. Let us suppose we have the reverse of this reaction, which is hydrogen combining with iodine to give you hydrogen iodide. Its K expression will be the concentration of Hi raised to the exponent 2 divided by the concentration of hydrogen times the concentration of iodine, and this is equal to 50. This reaction here is a reverse of the one before. Let's go and watch it again. Hydrogen iodide is decomposing to give you these species here. In the other one, these guys are combining to give you hydrogen iodide, and it works out that its equilibrium constant is equal to 50. Now watch this. For the reaction before, that was a value for the equilibrium constant. Watch this. If we took the reciprocal of this, 1 divided by that, it turns out to be 50. So this reaction had an equilibrium constant of this, which is equal to the reciprocal of what this is. So what is point to be made? The point to be made is this. If you have a reaction going in that direction, and you found its equilibrium constant, and you wanted to know what will be the equilibrium constant for the reaction going in the reverse direction, you take the reciprocal of that, and that provides the equilibrium constant. If you had this reaction now, and you didn't do that one above, and you wanted to know what would have been its equilibrium constant, you would have found the reciprocal of that, which will turn out to be that. For any reaction at equilibrium, its K value can be obtained by taking the reciprocal of the K value for its reverse reaction. The magnitude of the equilibrium constant. Now, the magnitude of the equilibrium constant gives important information about the relative concentrations of the products and reactants in reversible chemical changes, of course, at equilibrium. For example, if I have hydrogen combining with iodine, we just found that its equilibrium constant is 50. What does that tell us? Look, you're getting a large value, so you mean which one must be higher? The numerator or the denominator? Definitely, that value, the numerator there, must be substantial compared to the denominators here. This tells us that there's a preponderance of products compared to the reactants. I want you to see how the rate of reaction of iodine is same as the rate of reaction of hydrogen because they're reacting in a 1-to-1 mole ratio. 1-to-1. Notice how the equilibrium concentrations of hydrogen and iodine are low, but that of hydrogen iodide is extremely high. Of course, these things are not drawn to scale, so forgive us for that. Using bar graphs also, we can show how the product here predominates and you only have a small amount of leftover reactants here. In such a case, we say K is very much higher than 1. Another example. This is for the decomposition of water at 1000 degrees Celsius to give you gaseous hydrogen and oxygen. Look what the K value is. Of course, it's a negative 10. That means it's very low. Establishing the K expression for that, we're going to have concentration of oxygen times the concentration of hydrogen to the exponent 2 divided by the concentration of water vapor raised to the exponent 2. And that turns out to be that. So the question is asked, which one predominates? Because this value is so small, this must be very huge. So you're going to have lots of leftover reactants compared to the amount of products that are formed. Let's see from the graph. Yes, water decomposes like that, where you can see only small quantities of hydrogen and oxygen are produced. That's the hydrogen, that's the oxygen. Notice how the rate of production of hydrogen is twice that of oxygen, and the rate of decomposition of water is the same as that of hydrogen. In this case, you can see that the equilibrium is towards the reactant side. You have huge concentration of the water remaining there, and only small concentrations of hydrogen and oxygen being formed. In this case, K is very much smaller than 1. There's a third scenario where you're having nitrogen dioxide reacting with nitric oxide to give you dinitrogen oxide and oxygen at 500 degrees Celsius, and K for that is 0.914. You can see that this is nearly close to 1. The expression for that is that concentration here times the concentration of oxygen divided by the concentration of nitrogen dioxide times that of nitric oxide, and it turns out to be that. So which one you think is going to be slightly bigger? These here. These, the reactants, are going to be slightly greater in concentration than that. So we say in such case they're nearly equal, right? So you have your nitrogen dioxide and nitric oxide there. These react at the same rate. That's why you have only one line for both of them. These are the product being formed. You can see that they form at the same rate. That's why you have only one line. That represents the products, and that there represents the reactant. And we say that K is approximately equal to 1. This brings us to what is called percentage reaction at equilibrium. So in this first sample problem, we are having how hydrogen iodide is decomposing to give hydrogen and iodine in a 2 moles per liter to 1 mole per liter and 1 mole per liter. Mole ratios. Initially, that was a concentration of hydrogen iodide, and these here are the final concentrations of the species at equilibrium. That for hydrogen iodide, This for iodine, and that is for hydrogen. They want you to find what is the percentage reaction. This is the solution. If we had 2 moles per liter of hydrogen iodide, and this reaction went to completion, we would have ended up with 1 mole per liter of hydrogen and 1 mole per liter of iodine. Or if we had that concentration of hydrogen iodide, we should have gotten that concentration of hydrogen and that concentration of iodine, because every 2 mole is giving you 1 mole and 1 mole. Therefore, that concentration will give you half of what that is, which is this and this in both cases. And that's the point we're making here. Had it gone to completion, you should have gotten that for both hydrogen and iodide. But we got only that. The percentage reaction is equal to the actual yield divided by the expected yield times 100%. That was the actual yield, and your expected yield is that. Doing the math, it works out to be 20%. So your percentage reaction is this. Of course, because each of these here is produced in a 1-to-1 mole ratio, had you used the value for hydrogen, you'd have gotten the same thing. Let's do another problem, see where is a slight deviation from that. In this reaction, ammonia is decomposing to give nitrogen and hydrogen according to this mole ratio here, 2 moles per liter to give you 1 mole per liter and 3 moles per liter. You are required to find the percentage yield if you started off with that concentration of ammonia and you allow it to sit until equilibrium has been established. They will give you the final concentrations. So we started off with that, and just to review for you how they change, you're going to get 2x of that decomposing to give you x of that because it's 1 here, and you're going to get 3x of that because of the 3 there. When the mixture is analyzed at equilibrium, these are what were found to be present. Now you want to find out what is the percentage reaction. Had this reaction gone to completion, if you started off with 2 moles per liter, you would have gotten 1 mole per liter and 3 moles per liter. If you started off with that quantity, had it gone to completion, look, this is 2 to 1, right? For every 2 of this, you get 1 of that. So whatever you started off with here, you must get half of it here. Okay? So if you know this, then you just multiply this by 3, and that's what you get there. But look what happens. This is not what obtains. When you decompose this fellow here, you ended up with that and these quantities. Using nitrogen to calculate the percentage reaction, we have the following. Again, you take the actual yield divided by the expected yield times 100%. The actual yield was that, but we expected that value. So we take what we got divided by what we expected times 100, and it turns out to be 50%. Using hydrogen to find the percentage reaction, again, we take its actual yield, divide by its expected yield. That was the actual yield, and that was the expected yield, and you multiply by 100%, and again, it turns out to be 50%. So note how, if any product is used, the answer turns out to be the same. And that's how we calculate the percentage reaction for any reaction at equilibrium. Calculate what is the theoretical yield, and then take what is actually produced divided by what is expected times 100%, and we get what is called the percentage reaction, as was exemplified in both of these problems.